Thank you everyone again for joining us today for today's SMART webinar. Simi Oduwole is presenting today. Simi Oduwole is a master's student in petroleum engineering at Colorado School of Mines. Her research is on mitigating the effects of climate change by geosequestration. Under the SMART project, she probes the impact of carbon dioxide in the subsurface over time, using field measurements as references. She examines the effects of geosequestration on reservoirs and seals. Simi will be presenting today on reservoir analysis of a CO2 sequestration site, experiment-guided field-scale modeling. She'll be presenting to us for about 40 minutes, and then we'll open it up to Q&A and discussion. Simi, the floor is yours.
Thank you so much, Mia. Can you hear me correct?
We can hear you.
Okay, so thank you. Like Mia said, I attend Colorado School of Mines and I work with the CSM SMART team under the Task 2 initiative to see what happens in the reservoir based on well log data, lab data, and reservoir simulation. So I'll be sharing the results with you in this presentation. Okay, so briefly, I would like to describe the project to you, tell you about the motivation of the research, the information on the field, and basically the objective of the research, why it was done. And all of this was to understand first the fundamentals of what is happening in the reservoir due to CO2 and fluid interactions. And the results of this were used to, guide our machine learning workflow here in Colorado School of Mines. So I'll also take you through the data we have. We had some lab data given the analysis we had made with Bell Creek samples. I'll talk about the well log data that we had also gotten for the research and how the changes in the field correlates with that of our reservoir simulation as well, which had been guided by the well log data and the lab data that was gotten. I'll go on to explain the effect of the simulated changes to seismic and how we can better map CO2 saturation in the field, given some of the changes we had seen. I'll conclude with some few points that are very essential and critical for our further work here in Colorado School of Mines in our machine learning algorithms for CO2 sequestration sites. So to briefly describe the project, like I said, I'll talk about the motivation, the objective, and introduce you to the field. Our motivation was to combine lab and well log data to map CO2 saturation because we know that no data is complete in itself, and so a combination of data makes things better. And so combining laboratory and well log data of the field that had been undergoing CO2 injection will help us understand the fundamental changes in the CO2 field, and it can help in mapping CO2 saturation. So, and when we map CO2 saturation is because we want to prevent potential CO2 subsurface leaks that could happen. So the safety portion is also involved, where we want to know how CO2 is being transmitted within the reservoir and if it remains where it's supposed to be. So in understanding the leaks, we know that there are interactions between the original reservoir fluid and CO2. As has been stated in literature, like Lake mentioned that viscosity and density alterations happen when we inject CO2 into an oil reservoir. There are also changes in fluid composition, like Orton had also given in his study. So the effects of the fluid change could also affect the entire rock because the rock houses the fluid. And so we'd expect some acoustic properties to be altered, like Gutierrez had said, and like we have in our publication in the leading edge newspaper as well. So all of this motivation is to tell us that something is changing and it's not just the saturation effect. And so we go on to see how can we combine our laboratory log data and simulation to understand and better explain these changes. The main objective of this research is to quantify CO2 effects from seismic maps with reservoir simulation, lab, and log data. So if you look critically at this map here to the left, we see something quite unique. For the red triangles that are labeled as injectors, we see that there is a high amplitude difference. This is a seismic time-lapse amplitude of 2 years, compared to the circles in green, which are the producers, where we have low seismic amplitude difference. So this change, although Bunningston had expressed it as also due to homogeneity of the reservoir, which we also acknowledge, we just think that something else might be happening with the fluid. There could be fluid effects that have led to the different responses of the injector and the producer. I'll briefly explain where this field is located. Bear Creek oil field is located along the Montana-Wyoming border. Very soon I'll be zooming into five wells that are forming 5-spot pattern. These wells were used just because we need to understand and develop fundamental knowledge that should inform our machine learning workflows. Whatever representative of these 5 wells we have, we are quite sure that on a larger scale, it could be very effective in understanding the seismic map. The field stratigraphy here, it talks about the different formations in the field. There are very popular formations here, like the Niobrara carbonates here, right above the target for our CO2 EOR, which we are considering. And looking at this field, we see that the target is very good because it's majorly sandstone, high permeability, high porosity. CO2 is able to be transmitted into the reservoir quite easily. And it's below numerous feet of formation, that is, those ones above it would definitely allow for the safe storage and mitigate subsequent leaks over time. So our world is safe even as we inject CO2 into this reservoir. The field covers about 22,000 acres, quite a large field. And like I said, the reservoir is mostly sandstone. As shown here in Bunningston paper, we see that it has mostly sandstone, and the top part of it still has some silt, and that is why we have some permeability and porosity variation in the reservoir. So we have porosity that ranges from 15% to 35%, and permeability could be as low as less than 100 and as high as more than 1,000 millidarcy. The sandstone portion of the reservoir is compartmentalized according to literature, so there are permeability barriers that are present, some faults in this formation that allow for either more communication or no communication between wells. CO2 injection in reservoir formation has been since 2013, May, and the reservoir still produces hydrocarbon and water, hence why the Bell Creek is both an enhanced oil recovery field and a sequestration field. So it allows for the displacement of hydrocarbon and water. Given the time that this injection had begun, we have so much data, time-lapse seismic data have been done, well logs have been conducted. We had the well logs and we used it for our own numerical simulation here at Colorado School of Mines. So initially we started to say, let's understand what is happening in the fluid, and we better did that through laboratory analysis. We performed some experiments. NMR and acoustic velocities were taken on the Bell Creek, both as interacting with CO2 and just Bell Creek alone. So I'll be sharing the results in this section. The NMR results here showed that when there is low pressure of CO2 injected to the Bell Creek oil, we see that the NMR relaxation, the peak is quite flat, just broadly spread out. And then with increasing pressure, we see that CO2 affects the oil because we have a shift towards higher T2 relaxation times. So increasing pressure leads to increasing T2 relaxation times. And so an understanding of this is the viscosity of the oil is decreasing as we have increasing relaxation time, as you see in this plot to the right here. So we have increasing pressure leading to reduction of viscosity, and it's consistent with literature as had been referenced here in the slide. However, something quite unique happens when the pressure is increased up until the liquid phase of CO2. So when it transfers from the gaseous to the liquid state, something happens. There's a shift of the oil, of the main oil, heavier portion of the hydrocarbon towards lower relaxation time, and a new peak comes up here to the right at a higher relaxation time, which is quite separate from the entire peak we'd always had. So this is something that is kind of showing to us that, as literature has said, when we inject CO2 into oil, there is the lighter hydrocarbon portion of the lighter fraction of the hydrocarbon mixes with the liquid CO2, and so it's distinct in the NMR response here. So we see the fluid segregation in our own laboratory data, just confirming what has happened in literature. So going on from that, we had said, okay, if there's a fluid segregation, can our acoustic velocity, account for this? And just as a sample, as a way of referring, here is the left-hand side here is the compressional velocity versus pressure plot, where we have the compressional velocity as a function of increasing pressure. What is seen here is that there's a direct proportion. The compressional velocity value increases as you increase pressure. But when CO2 is injected into that same oil, the Becquerel oil, what happens is that we have some competing effects happening here. Generally, you see that when it's gaseous, there's a slight increase, but not so significant. And then in liquid, we have a drop towards the minimum miscibility, around the minimum miscibility pressure, and then a gradual increase, which is just a slight increase compared to, when it's crude oil alone, where we just have the very huge increase all the way to 1560. So here we see something happening, that crude oil and CO2 allows for velocity dispersion effect, and this can be due to CO2, the viscosity change, and it's quite significant here in the laboratory data we've gotten. So moving on from the laboratory data, I wanted to see what is happening in the field. How can the field explain, we had seen fluid segregation, we had seen dispersion effect due to CO2 in oil as well. And so can our field data, if we get some well log analysis, can they explain this effect? I'll be evaluating the formation with the well log data and show you some neutron porosity time lapse that had been gotten and how those can explain the CO2 effect in the reservoir. Looking at the formation here, we see that the muddy formation is highlighted in purple, the top is in brown, the bottom is in blue. The reservoir section has been picked from triple combo and sonic logs, just for the sake of accuracy. And when we look at each of these wells, it's interesting to note that the reservoir tops had different depths. So the deep is obvious in this field. So it has also been confirmed in literature that there was a dip in the northwest direction, and so we have our well logs telling us that. Interestingly, like I said earlier, we have silt above the sandstone portion of this muddy. And when we look at the gamma ray responses, the higher gamma ray is the silty portion, and just above the lower gamma ray where we have the more permeable and higher porosity sandstone. So after characterizing the reservoir formation, the reservoir portion of the wells using the well logs, we had gone on to see the change happening using neutron porosity time lapse. Here I'll be explaining two wells that are representative of the entire log data. We have an injector and we have a producer here. So the muddy formation is within the blue bars shown here, and when there's an increase in neutron porosity, it's color-coded with purple, and a decrease in neutron porosity is color-coded green. So going with the injector, it's interesting to find that within the MODI, the high permeability zone and high porosity zone has the greatest change, and we'd expect that because CO2 would preferentially just move through the easiest flow path and not go through the low permeability area. So it's interesting to find that neutron porosity decrease was observed in the injector, quite significant because we have it all the way to as greater than 20%. So the decrease in neutron porosity value when comparing the neutron porosity measurement before CO2 injection and after CO2 injection shows that something is happening. CO2 is coming into the reservoir, displacing hydrocarbons, because neutron porosity generally measures the total hydrogen index of the formation. And so the non-hydrogen containing CO2 definitely reduces the hydrogen index when it displaces the existing hydrocarbon. But to the right here, we see the producer, and it's interesting to find that there seems to be very little to no change in the producer. This change is below 10%. We could assume it was within the error margin of the tool. So our understanding of theory was that if we had CO2 mixed with hydrocarbons, neutron porosity logs should definitely decrease in both wells. However, like I said, the injector alone had the highest response and producer showed little to no change. So we went on to see if we simulate CO2 interaction with oil in the model, can we explain the reasons for which this is happening? Why do we have the producer not show so much response as the injector does? And so I'll be defining the model to you, showing you the constraints and parameters of the model, and discuss the results of the model with you. So like I explained earlier, just to reiterate, the model was guided by all of the experimental and log data. So you can see here that the dip is shown in this reservoir because we had a dip in the field. And like I explained earlier, I will be going into 5 wells. So it's a 5-spot pattern just for the sake of understanding the fundamentals, which we can then apply to the entire field. The well spacing is about 400 meters in between. So each of the wells are equidistant from one another. And the reservoir thickness is about 60 feet. We had made 6 layers of reservoir to allow for gravity effect as well as buoyancy. And then the reservoir pressure was in line with the original pressure of the Bell Creek field, which was about 2,400 psi. The reservoir temperature we had gotten from lab data of 107 Fahrenheit. The oil API gravity as reported in literature is about 37. Showing it's light oil, although it contains a bit of 5% heavy oil, which are termed asphaltene because the heavy oil component eventually lead on to forming the asphaltene. So the simulation was done above minimum miscibility pressure, and the average CO2 injection rate was about 2.3 million cubic feet per day. We had gotten the injection rate from data shared with us during the from the SMART team as well to typify the field. So looking into the model, we had some properties starting with the fluid. Here we see the fractions of the fluid, the crude oil fraction from C1 all the way to C36 plus. Individual by individual basis, we see that the methane has highest amount of composition, about 19% of the mole fraction is methane. But when we group it according to, light, intermediate, and heavy, we see that the intermediate portion is of higher mole fraction in the entire crude oil. However, I'd like you to notice the C36 plus of 5% here because it's been reported in literature that the displacement of the entire hydrocarbon is driven by the displacement of the heavy portion of crude as well. So we went on to look at this heavy fraction C36 plus in the reservoir simulation. So starting with the correlation of our model with well-log data to understand what is happening and the reason for which we have the producer show very low response compared to the injector, like I mentioned earlier. You see here that the oil saturation with time had so we see here that the oil saturation with time had been not I'm trying to move my change your cursor. Okay, so for some reason, sorry, my animation is not showing. So, but what we observed is that the oil saturation that we had modeled out wasn't so much of a difference after 5 years around the producer compared to the injector, which had lost so much. So at the injector, the oil saturation had moved all the way from the initial oil saturation to residual oil saturation. But at the producer, we still had some significant amount of saturation around the producer. So perhaps, the presence of that significant amount of oil around the producer is the reason for which our neutron porosity did not detect the presence of CO2 around the producer. But since that the hydrogen content, the hydrocarbon content around the injector was almost fully displaced, it had seen the CO2 effect around the injector. So going from this, after correlating our numerical model to our time-lapse data, we understand the fact that the neutron porosity measurement was also detecting the CO2 effect based on the injection and the data we had. So we went on to see in our model the fluid segregation that had been accounted for in the literature. So there is spatial fraction distribution after a year showing here in our left figure. In the left figure, we see that the C6 fraction had moved was about 80% saturation around the producer compared to the C15, which was about 60, C20, which is about 40, and C36 plus, which is about 20%. So what happens is, from this, we see that spatially there's a preferential displacement of lighter hydrocarbons, and our model confirms that that has been reported earlier in the literature. And when we go on to consider the depth distribution vertically, what is happening? So in the initial model, when t equals to 0, we expect nothing to happen. We do not expect that there is a displacement at that time. But in 5 months, we see the incursion of CO2 from the injectors towards the producer, and it had moved further in 10 months. So yes, our reservoir is transmitting CO2, but what happens with the crude oil fraction? Does it still have that preferential displacement vertically? And this is shown here in our result, that the injectors are moving, are displacing C6 towards the producer faster than C36 plus, even within months here. So our model confirms that there's this distribution of fraction that is preferentially allowing the lighter hydrocarbons before the heavy hydrocarbons time. And we are modifying our own concept, our understanding, because our understanding had been having CO2 sort of homogeneously mixed with the entire hydrocarbon. But with what we have, with what literature has said and our confirmation from our model, we understand that there's a viscosity change that segregates fluids, allowing for the lighter ones to be displaced before the heavier ones. Okay, so going from this, how can our understanding of the segregation, how can our understanding of the viscosity change, how can we correlate it to rock and fluid changes and also to seismic? And those are what I will be showing you in our next session. So we went on to extract the fluid viscosity and see what happens in 2 years and 6 years. So in 2 years, we see that there is a pattern forming of a slight change around the injector compared to the producer and the diagonals. But in 6 years, it's more obvious. Bear in mind that I said that the reservoir has some dip, and so we have the shallowest portion as this injector here to the end. And so we have some kind of slight differences in injector responses due to this dip. But overall, we see that the injectors had a decrease in viscosity because CO2 comes in and displaces the hydrocarbon, and this is also in alignment with literature that the effect of CO2 is reducing the viscosity of hydrocarbon. I put in the 2-year time-lapse seismic amplitude difference here just because I want to be comparing our 2 years time-lapse simulation with that of the seismic amplitude difference. The amplitude difference has been between the shale above, which is the Maori, and the muddy below it. So comparing this, we see that the viscosity in 2 years hasn't really given us so much, to look at, and compared to the time-lapse amplitude of the seismic data. What happens with fluid viscosity, fluid density? Can we see something that is quite different in density? So in 2 years, we see that the pattern is beginning to form around the injectors where we have a decreasing density. And when we come here to the 2-year time lapse, you see that it's almost about the same pattern around the 5 spot. Like I said, just 5 spots were being used for this study. So around this 5 spot, we see the pattern that is being formed. And in 6 years, it's clearer to see that the injectors had lost most hydrocarbon, and there is sort of a density built up coming up around the diagonals and the producers. So because mass is conserved, whatever lives somewhere goes somewhere. There is no disappearing. So we have the heavier the hydrocarbon that had been displaced from the injectors move towards the injector and the diagonal. So after confirming that what we know about viscosity and density in literature tallies with our own model, we went on to see the effect of this in our C36 was the heavier portion, because we understand, like I said, that the displacement of the heavier portion affects the displacement of the entire corridor of the reservoir. So in 2 years, we see that the injectors were beginning to have reduced saturation of the C36 plus. And in 6 years, it's interesting to find that the injectors had, basically lost almost all of the C36 plus, but it had accumulated at the diagonals because the producer here in the middle has a lesser amount of C36 plus. So that is the accumulation we have. And in theory, this is in theory, right? But when we come to reality, we would expect that the injector is not just a point source. So boundary effect can be the reason why we are seeing that, the injector here is losing almost all of the C36 plus, because in reality, it could be that there's an accumulation of the C36 plus around the vast expanse of the injector. But when we compare the 2-year time-lapse responses, the seismic amplitude difference here was the pattern we have is similar to that of the C36 plus. So in addition to the fact that density is showing us something, C36 plus is also showing us something that is ongoing, that you can correlate with the seismic data. And this is interesting to find that, all of these bits of interesting facts are those things that we tie up together for our own machine learning here at Colorado School of Mines. So we went on to see geophysical models of impedance and understand, can that explain in total, everything happening? But we see that in 2 years, we're not having so much, it's beginning to appear, but we don't have so much of a well-defined difference around the injector to show us the movement of CO2. In 6 years, we see that there is a decrease in the impedance because, CO2 and CO2 had displaced most of hydrocarbons, particularly around the injectors. So the impedance is just trying to explain it, but not entirely explaining everything. So it's basically like needs so much it needs the contribution of many other things that I'd explained earlier, and then I'll be talking about one more, which is the Gassman-Bock modulus, trying to explain, using the saturation idea to explain what is happening, change in saturation, where we bring in CO2 to displace the fluid. So we're not basically comparing interactions between components here. We're rather comparing like the bulk fluid interactions in Gassman bulk modulus. So when we look at the bulk modulus here, the map in 2 years isn't very clearly showing the map pattern that we have in 2 years time-lapse amplitude. But in 6 years, we see that there's a huge decrease in the bulk modulus, and we'd expect this because CO2 is of lesser density than hydrocarbon. So all of this together, all of the viscosity, the density, and bulk modulus and impedance change have shown us that there is both fluid effect going on in the reservoir, and that just one model is not enough in explaining all of this. So in conclusion, I'd like to say that how can we bring in all of these models in understanding our seismic data? When we have seismic data from the field, will viscosity help us? We know viscosity is influenced by phase quantity because we have CO2 just coming and shown at the injectors that there is a very huge decrease, but around the producer and the diagonals, we didn't really see so much effect in 2 years. Will bulk modulus and impedance model help us? We see that it's not so adequate for determining the fluid compositional changes. So it needs more than just using that alone in understanding what is happening in our seismic data, which represents the CO2 effects in the field. Can we put in density? Density considers fluid segregation effects, like I explained. And so that alone in itself may not really show it because, the fluid alone cannot explain what is happening in the reservoir. We need to input the rock properties as well, for which we had used the geophysical models also. Will the heavy crude, which dominates displacement of hydrocarbon, will it also help? It's interesting to see that the pattern in C36 plus fraction is even more visible, in 2 years compared to others. But we believe that seismic data can have so much correlation with all of these properties of density, C36 plus saturation, viscosity, bulk modulus, impedance. All of this can come together to help us understand what changes we see in seismic data. And so our laboratory analysis of fluid interactions, when we get our fluid from any reservoir, although this work has been done with an oil reservoir having CO2 injection, but even when we go further into maybe saline aquifers, we'll still need to understand interactions of fluid, model the fluid, understand the property changing in our fluid models, and geophysical models bring in the rock fluid interaction that we need, which is dependent on fluid component interactions. Because like I've shown you in these slides, we see that the components of the fluid, like components of hydrocarbon, are migrating preferentially. So the component interactions are important for our geophysical models. And when we add field data to indicate CO2 saturation, we can bring this also into our simulation to understand the fluid component interaction. So we have all of this coming together to feed our machine learning workflows here at Colorado School of Mines. And we believe that a guided machine learning based on all of these reactions will present, perhaps a closer to reality result than just having saturation-based machine learning workflows. So, in conclusion, I would say injectors and producers have varying seismic responses, like has been shown by the well-logged data and also by numerical simulation. We understand that fluid saturation alone cannot explain the observed changes because there's so much more going on within the component by component basis. The mobility of oil components can better explain for the seismic data. We had seen in the 2-year time lapse where, the C36 plus heavy fraction had shown similar pattern of displacement as we have in our seismic time-lapse. The machine learning workflows must incorporate fluid-related effects in CO2, EOR, and CCS operations, because we know that there's fluid segregation and accumulation that has been determined by this study, and also consistent with literature. We know that fluid density and viscosity leading to velocity dispersion can affect our modeling. Grain cementation could also be happening, because when we leave back the C36 Bell's fraction, we have, the more viscous and asphaltic kind of hydrocarbon left, which can allow for the sticking together of grains. So we can have that grain cementation, and would need to understand what frame stiffening is. And eventually the fluid mobility, all happening when these effects are going on, because when you're changing the grain cementation, you're changing permeability, you're changing so many things, and relative permeability changes, and all of this will be incorporated into our machine learning workflows. So our machine learning workflows will benefit from all of this study, and it will give us a more, closer to reality result. So I acknowledge the sponsorship of DOE, the data of ERC, the CMG team for giving us so much guidance in the modeling, the CSM Smart team for putting in the thoughts, the work, and the CRFM family. And here are my references. I thank you for listening, and I welcome questions.
Thank you, Simi. We will now open up the webinar for questions and comments. Participants, you can put a question in the chat. You can also unmute yourself. And there's also a raise hand function, and I will call on you if I do see a raised hand. Any questions or comments?
Yeah, I have a comment. This is Fred Amzadeh. Monica, you gave an excellent talk. I really liked it. I have a couple of comments. One is, as you know, although P-wave velocity and possibly S-wave velocity changes can be observed from seismic data as far as presence of CO2, but they may or may not be as prognostic on the amount of CO2 in the compartments or saturation. So have you had some analysis on how to handle that, and also if some alternative methods could be combined with the P-wave velocity changes that you see on the CO2 sort of being present in the compartment?
Yes, we have. And if I may get your question correctly, like I said, the effect of, are you trying to talk about the quantity of CO2 in the reservoir?
Right, right.
Okay.
So basically, I'm referring to something called about fizz gas on the conventional type gas reservoir.
Oh, okay. So in terms of quantity, we're still working on that because we have not done quantity. But in terms of the effect, yes, we've done that as shown in this slide. Right.
So I think sometimes it might be important to see how much saturation or amount of CO2 is being observed. On a somewhat related topic, you probably did not, I didn't see much work on potential analysis of Poisson ratio. Did you have any work on that?
No, we're not able to do that yet, but thank you for that idea. Yes, we'll look into that.
Okay, but the last question is, in this particular case, you did not have any microseismic data or for that matter, dipolsonic logs to look at them?
No, we don't have that data. Maybe if the smart gives us, yes.
All right, thank you.
Thank you.
I'm noticing a comment in the chat to Fred that they do not have the seismic data yet, so the quantification is still pending.
Okay, yeah. What I was actually going to suggest that even if seismic data is there, seismic is not as effective in measuring the quantity of CO2, and you may need either density information. Shouldn't say seismic, just the P-wave velocity is not effective. Either you need density sort of variation and or maybe control the electromagnetic type data. So to be combined by seismic.
Thank you so much, Fred.
Any additional comments and observations?
Yes, I have a question, Simi. Thank you for the very nice presentation. So my question is, have you taken into account, or will you take into account, the reservoir heterogeneity that may, exist between the various wells you're looking at? And I can follow up by saying, if you have all those well logs, then you have a great opportunity to explore that in terms of, let's say, porosity, permeability, all these, putting them in your geocellular model.
Okay. Thank you so much. Yeah, that's also part of the plan, but I've not put in that in this slide. We're trying to say, just like you said, if we're having grain cementation, porosity is changing, permeability is changing as well. And so we need to refine our results in line with the heterogeneity of the reservoir. So yeah, thank you.
Monica commented in the chat that the plan and suggestion to us all is to use other models to Gassman and combined with EM data to quantify saturations. The point was to be cognizant of effects to be modeled. Prakash, your hand is raised.
Hi, Simi. This is Prakash from Penn State. Thank you so much for the presentation. I really enjoyed it. A lot of good work. I was wondering, do you have any comments on the sparsity of field data for machine learning purposes? And how do you or how should we envision using or incorporating it as we build these frameworks of machine learning and still incorporate field data or lab data?
Okay. Thank you so much, Prakash. So basically, the machine learning team here in School of Mines is also struggling with sparsity of data, and it's all over. But I think what we are just trying to see is if we can supplement, log data with some lab data as well, and also from simulations. Basic simulations like this give us some result, right? And so if we can supplement some, information from our models like this with the log data, it can help build our machine learning, even if we don't have so much data from the logs. Does that answer your question?
Yeah, I think that's right. Incorporating simulations that can be anchored on field data, and then perhaps building the machine learning frameworks on those simulations. Yeah. Great. Thank you.
Thank you, Parker.
Just checking. Michael Gross, did we answer all your questions? I'm not seeing that he's dialed in at the moment. Any other comments or questions? I'm not seeing any additional hands raised or chats. Participants, please feel free to unmute yourselves. All right, well, if there are no more questions or comments at the moment, please feel free in the future to reach out to the Smart FE email for additional follow-up questions, comments, or if you do have an idea as well for a future SMART webinar. Thank you, Simi, so much for the in-depth presentation.
Thank you.
And we have recorded today's webinar. And I hope everyone will please join us in 2 weeks' time on October 28th for the next SMART webinar. Thank you, everybody.